Hello, this is the first video of a third Matrices series for OCR AS Core Pure Further Maths, and it gives an introduction to inverse matrices. In a previous series, we learnt how to multiply matrices and what a 2 by 2 identity matrix looks like. Here we are trying to find a matrix such that when we post-multiply a given matrix, we obtain the identity matrix as the product. We can do this by solving the simultaneous equations that arise when we do the multiplication. So, for example, 2a plus 3c must equal 1. In terms of we're multiplying the 2 by the a, the 3 by the c, to give us this element of 1 here. Similarly, we get that 2b plus 3d must equal 0, and a plus 4c must equal 0, and b plus 4d must equal 1. Now, if we take these two equations, we can eliminate. So we've got the 2a plus 3c equals 1. And if we multiply that second equation by 2, we would have 2a plus 8c still equal to 0, giving us, if we eliminate by subtraction, that 5c would equal minus 1, and c equals minus a fifth. We can do similar calculations to find the values of a, b and d. These values turn out to be that a equals 4/5, b equals minus 3/5, and d equals 2/5, thus leading to the matrix 4/5, minus a fifth, minus 3/5, 2/5, as shown here. You may wish to pause the video here and confirm that pre-multiplying by this matrix to the original matrix also gives the identity matrix. Currently we have only looked at 2 by 2 matrices, but we will move on to looking at 3 by 3 matrices in due course. So if that matrix 2, 3, 1, 4 was called T, then our new matrix must be the inverse of T. We would write this as T to the minus 1, and this is equal to the matrix that we found. We can also take that fraction of a fifth outside of the matrix and say that it's a fifth of 4 minus 1 minus 3, 2. You will note that t to the minus 1 is the same as t to the minus 1t, both of them equal to the identity matrix. You may remember that generally AB does not equal BA, so commutativity is not normally the case for matrix multiplication. However, you should note that multiplying a matrix and its inverse is commutative, and that this implies a unique inverse. You should also note that only square matrices have inverses. These same points also apply to the inverse of a 3 by 3 matrix. So in this example, if we have a and a to the minus 1 defined apart from the constants p and q, we would be able to find p and q by using the fact that a multiplied by a to the minus 1 would give us the 3 by 3 identity matrix. There are, of course, a number of possibilities for taking the elements of a multiplied by a to the minus 1 equal to the 3 by 3 identity matrix to solve for p and q. One possibility is to multiply the first row of a by the first column of a to the minus 1. We would find that we had 2 times 5 plus minus 1 times 1 plus 2 times p, which would give us the first element of the identity matrix, so must equal 1. That would lead us to the fact that p equals minus 4. There are also a number of possibilities for finding Q. If we chose the third row of A and multiplied it by the third column of A to the minus 1, we would have that 1 times 7 plus 3Q plus 2 times minus 6 would also give us 1. This would lead us to the fact that Q equals 2. But we could have used any combination of rows times columns, which included P and Q, knowing that A times A to the minus 1 equaled that 3 by 3 identity matrix to work out the values of P and Q. In the next session, we will explore the inverse of 2 by 2 matrices further and introduce determinants.